Chapter 7, Bitwise Operators. Hello everyone. Welcome to Browning's Introduction to Programming with Python, 5th edition. We're looking at Chapter 7, Bitwise Operators. This will build on what we did in Chapter 6, your logical operators. And what we'll find is they work in a very similar fashion. However, they work on the individual on and off bits. If you think of 8 bits to a byte, and then you have a series of on and off pattern, then the bitwise operators actually do their comparison on those individual on and off bits. But we're jumping ahead a little bit. Let's kind of look and see how that goes. So Chapter 7, all languages, programming languages have some type of bitwise operators. Python is no different, and they of course work on the ones and zero, the on and off, which the machine makes the computations based on those bits. The bitwise operators evaluate numbers as sequences of binary bits. Bitwise operators are very similar from what you just did in the previous chapter, except they work on a smaller scale, and there's a little bit of difference in there, but not drastically. For most of our examples, we will be using a word size of 8 bits to a byte. Those are terms that you'll hear used. There are 7-bit machines, but most are 8-bit now. So 8 bits of on and off, which would make that decimal value, which would ultimately, in say an ASCII table or a UTF-8 table, would translate to some other character. Alright, first one we want to look at, the bitwise exclusive. We will have an inclusive, but exclusive XOR. Alright, the bitwise exclusive or XOR operator in Python is represented by the caret. It's a little arrow facing up. Unlike the logical OR that we have used before, bitwise exclusive OR will find a condition false if both are true. So that's what you want to underline and highlight and kind of get straight in your head. Remember with our previous OR, one or both sides could be true and the whole statement will be true. With an XOR, only one side can be true. If they're both true, it's a false condition. Now, if you related this back to electronics, and remember we did say that software design and these truth and false conditions ultimately related back to electronic, components, which would either be on or an off state, like, so for example, like a transistor or something of that nature. If you had an XOR, it could be that you had, say, voltage coming in from 2 different sources to, maybe light a light bulb, all right? 5 volts coming in one side, 5 volts coming in the other. Well, if you had both conditions true, you'd have 10 volts, and for, say, a 5-volt light bulb, the light bulb would glow. So an XOR condition is actually valid because you only want one, not both, to be true. This is a little different, again, than what we did in Chapter 6. So try the example out, the hands-on XOR, and what we have is x equal to 1, y equals to 1, and then we're asking the question, is it true that 1, are they both true? Alright, try that out and then hit pause and we will resume. Alright, very good. So if you notice, it doesn't print the statement. Why? Because both are true. Remember, 1 is true, 0 is false. Actually, any positive integer is true, 0 is false. They're both true. You can't have true on both sides with an XOR, so the print does not print. If you changed one of them to a 0, of course it would work fine. Alright. Now, let's look at the next thing that we have up for bid. More with XOR. Let's try that out. Notice it prints a false. Now, we didn't have an if statement. We're not checking for a condition. We're just trying to see if they're true or false. That's why it's printing the false. Okay, because they were both true. We said with an XOR, both sides can't be true. It's a false condition. Happy days. Now, to look at how this works, this is really, really interesting. We'll go through this series of steps here and kind of think this out. But again, we said that 8 bits to a byte, 0 for false, 1 for true. And we have our 2 numbers represented here. Alright. And what you're going to do is literally go from top to bottom and do those comparisons. And if they come out true, then you'll write down a 1. If they come out false, you'll write down a false. So you can kind of work through this. And if we're going from left to right, 0 over 0, false over false. So we're going to have a false condition, have a 0 down there. True and false, the second one over from the left. Well, one side could be true with an XOR for the whole thing to be true, so we have a 1 beneath it. All right, third one over, false with a 1 true beneath it. That's okay for an XOR, so we put a 1 beneath it. So you kind of get the pattern there. This is how this evaluation is taking place. We're just doing it manually right now, but you'll see that it's pretty easy to do. Work through those steps, and you'll see how that works out. All right, now let's try that out by hand manually with the next example where it says hands-on practice with Bitwise XOR number 1. Hit resume when you've completed that. All right, very good. If you want to look at a truth table for how that operation takes place, you can see that. Basically, they're both false, it's false. One's false, one's true, it's true. One's true, one's false, it's true. Both true, it's false. All right. Now, multi-bit numbers. Let's assume that we were doing this with 3 numbers and we were trying to do the comparison. We have an example on the next page where you'll see how this works out. And then the second thing that I want you to kind of think about here is if you'll start your Windows calculator, if you're using Microsoft Windows. If not, you can use an online calculator. But get one that does scientific mode that will allow you to switch between decimal and binary. And what you can do is go to binary, type in the number that you see there, switch it back to decimal, and you'll see 3 in binary is 1 1. Now keep in mind here, we said that 8 bits to a byte, if they're non-significant bits to the left, they're dropped, so you'll need to pad those manually. So you can imagine that 3 in binary on, you'd actually have 6 zeros padded off to the left, non-significant bits. All right, let's try this out and just see how this works from an interactive prompt. And also I want you to try out the Windows calculator as well. We have an example here, print 3 caret 13 caret 21. A result of 27 prints, which in binary is, yep, you got it, the number right up top. Try that out if you would with your calculator and from an interactive prompt, and then hit resume when you're ready to go on with the rest of the lecture. Alrighty. That was pretty interesting if you think about it. I think probably you're inside the machine's head a little bit more now, trying to understand how it works. Let's try the practice on XOR number 2. Alright, we have 1 caret 3 gives a result of 2. Fill in the blanks with the example. Try interactive mode. You could do this from a script if you wanted to, but it's just easier to do these one-line programs from interactive mode. You'll find it's very handy to switch back and forth on Python between the two. But try this out if you would. Go through the steps and then switch to binary mode, and you'll find a result of 2. Hit resume when you're ready to continue with the chapter. Okay, next example, bitwise inclusive OR. So this is not XOR, but inclusive OR. Bit different than the exclusive XOR. It will return true if both operands are true. So this is similar to what you did with the logical OR. All right. Now, the way you're going to do this is with the single pipe sign. All right, on your keyboard. So we have X is equal to 1, Y is equal to 2, and then we have our statement that we're asking. Is it true that X is equal to 1, or is it true that Y is equal to 2? All right. So try that operator out if you would, and hit pause when you're ready to move on. Very good, very good. Alrighty, we can work this out on a truth table, or not a truth table, but by hand like we did before. If you look at the hands-on practice there, you'll see how that works. But basically, if both are true, it's true. So you can go through that example. False and false is a 0. True and false is a 1. False and true is a 1. True and true is a 1, because it can be true. Alright, try that out with that practice with inclusive OR number 1. And you should get a result of 3. Hit resume when you're ready. Alright, the AND operator, bitwise AND, it's a single AND sign, performs a bitwise AND on 2 integers in this particular case. Format, operator 1 and operator 2. We can do the same thing, but again with an AND, both have to be the same. So if you look at the example there, proving 6 and 3, It's only really the second place where you have true and true is true, and then you can actually have a true condition for the result. The rest would be padded out false. All right. Again, it's going to work the same logic as what you did in the previous ones. Let's try Bitwise Inversion, the tilde operator, upper left-hand side of most of your keyboards. If you look at the tilde operator or the complement operator, complement operator is used to invert or change all the bits of the operand, and it's just like what you would imagine. You're literally flipping the bits if you think about it. Okay, we do this from an interactive prompt. You can try that out. So we have tilde 6 gives the result of -7. Why? Bitwise inversion of the operand. Okay, so we're flipping those individual bits. To continue on with that, we have our shift operators, the double alligators to the left, double operators to the right. And basically, if you could think of what we're doing there is we're moving bits a certain number of places left or right, or if it's a true bit, say the first bit rightmost spot was turned on, we shift it to the left 1, it would make the leftmost bit next to it on and its previous bit off. All right. You'll see this used a lot with like flag variables and things like that. Maybe if you have a file and you right click on it or control click depending on the operating system, maybe you're setting a read-only property or a hidden property. A lot of times those are actually you're shifting bits to hit those flags on and off for the file. So if you look at the example there, interactive mode, 2 double caret to the left, or alligators to the left, 2 gives 8. We bring up our calculator again, we look at 2 in binary. You see it's represented by a 1, 0, and of course padded to the left would be 6 characters. However, left shifting it by 2 bits, 2 positions, would give you 1, 0, 0, 0, 0, right? And what is that in decimal? We'll switch it back with the calculator, and there you go. So let's try this out with the hands-on. And you can use idle and interactive mode again. Have your Windows calculator up. Try through the steps there and you'll see how that works. It will go left or right depending on whether you have the alligators facing left or right. Try the terms that you see at the end of the chapter, the activities, and expand on some of the examples if you want to. The more you do, the better off you're going to get with this stuff. And I will look forward to talking to you in Chapter 8. Have a nice day.